Hello everyone, welcome to another lecture on a material science class. Today we will be discussing lecture 5, which is on atoms and ion movements in materials. So the learning objective of this class is that by the end of this class, you guys should be able to understand temperature influences on the kinetics of diffusion and explain the principles and applications of diffusion in materials. So solids are an illusion of stability, and to naked eyes the materials usually appear static and stable. But at atomic level they are dynamic, chaotic, and constantly flowing to minimize energy. There are many cases where we wonder why these materials behave in the way they behave. For example, why does aluminum oxidize but not rust like iron? How do plastic bottles keep soda fizzy? How do we harden the surface of steel gears without making the whole gear brittle? And why do tungsten light bulb filament eventually fail? So these kind of questions can be answered through the concept of diffusion. Just as water flows from mountain towards the sea to minimize its gravitational potential energy, atoms and ions have a tendency to move in a predictable fashion so as to eliminate the concentration difference and produce homogeneous uniform compositions that make the material thermodynamically more stable. Different types of atoms or ions typically diffuse or move within the material to minimize the concentration differences. And diffusion is just the observable net flux of atoms or other species. And it depends on the initial concentration gradient and temperature. So diffusion can be defined as the diffusion of net flux of any species within a material. By any species, it refers to ions, atoms, and electrons. The driving force here is the concentration gradient. So the atoms diffuse to minimize the concentration gradient with the ultimate goal to produce homogeneous compositions that are thermodynamically stable. So in this case of water flow, water flows from high gravitational potential to low to balance the potential difference. Similarly, the chemical concentration or the concentration gradient, the atoms in high concentration tries to diffuse into low concentration to have the to balance the concentration difference. There are different applications of diffusion. In material processing technologies, the control over the diffusion of atoms, ions, molecules, or other species is very important. There are hundreds of applications and technologies that depend on either enhancing or limiting diffusion. For example, carburization for surface hardening of steel is one example. Dopant diffusion for semiconductor devices, conductive ceramics, manufacturing of plastic beverage bottles, oxidation of aluminum, and coating of thin films. They are some of the examples of diffusion. In the ones that are highlighted with green color is where we want diffusion to happen to help with the material properties, and ones with the reds are the cases where we want to avoid diffusion to get some performance of the material. So we need to understand the difference between drift and diffusion. Both of them cause the movement of atoms, ions, or molecules. The movement that is caused by the concentration gradient and temperature is referred to as diffusion, while the movement caused by driving forces other than the concentration gradient are drift. The driving forces could be density, electric field, or magnetic gradient in case of drift. Atoms and ions in their normal position in their crystal structure are not stable or at rest. Instead, they possess thermal energy and they will always move. An atom may move from a normal structure location to occupy a nearby vacancy, or it can also move from one interstitial site to another one. They may also jump across grain boundaries, causing the grain boundary to move. So, for example, in vacancy diffusion, an atom from other location in the crystal might see a vacancy and try to jump into that location. In interstitial diffusion, another small atom might try to fill in the gaps between the structure and cause diffusion. The ability of atoms and ions to diffuse increase as the temperature or the thermal energy possessed by the atoms or ions increases. The rate of atom or ion movement is related to temperature or thermal energy by Arrhenius equation, which is given as rate is equals to C naught and exponential minus Q by RT, where C naught is a constant, R is a universal gas constant, which is 1.987 calorie per mole per Kelvin. T is the absolute temperature as measured in Kelvin, and Q is the activation energy that is required to cause an Avogadro's number of atoms or ions to move, and activation energy measured as calorie per mole. There are different mechanisms of diffusion. Vacancy diffusion, as shown earlier, is one of those, where atoms swap places with vacancies. So this atom change position with vacancy, and this kind of mechanisms require high energy to break the bonds. The interstitial diffusion, the smaller atoms such as carbon, hydrogen, nitrogen, they squeeze past the host atoms, original atoms, and since they are smaller and is relatively easy to move between this interstitial position, the movement is faster and lower energy barrier is there that can be overcome with smaller energy. So that brings us to the concept of activation energy. So when one atom tries to squeeze past the other location, such as this atom trying to go into this vacancy position, there is some energy that is required to have that movement. And similarly, for this interstitial atom trying to squeeze past these atoms and move into other structure, there is some energy that is required to have that movement. That energy is referred to as activation energy, and usually more energy is required to for an atom to substitute from one location to other, or vacancy diffusion, versus the one case where we have a smaller atom moving fast, the bigger one. So larger energy for substitutional diffusion, while smaller activation energy for interstitial diffusion. The next topic is rate of diffusion, which is also given by Fick's first law. The rate at which atoms, ions diffuse in a material can be measured by flux, which is written as J, and flux can be measured with Fick's first law, which quantifies steady state flow. And if there is a flow of material from high concentration area to lower concentration area over a unit area, Fick's first law says that J is equals to minus D dc by dx, where J is the flux, which is the number of atoms passing through that unit area per second, and its unit is atoms per centimeter square times second. The negative sign indicates that the concentration changes from higher concentration to lower concentration. D is the diffusivity, which is a constant that represents how easily atoms move, and has a unit of centimeter square per second. And dc by dx is basically concentration gradient. C is concentration, the x is the location over time, location change in location. It gives the stiffness of the concentration of the slopes, and the concentration gradient has the unit of atoms per centimeter cube times centimeter. That said, the concentration gradient shows how the composition of material varies with distance. Delta C is the difference in concentration over the distance delta x. The flux at particular temperature is constant only if the concentration gradient is also constant. So in this case, if at some part of the material the atoms are only of type A, while in the other side there are a mix of type A and B, and there is a region in between where there is a diffusion of type A into B or B into A. So if you look into the percentage coverage of atom A over time T over distance D, we see that initially for this region we only have type A, so the percent of type A is 100, and at this location we have certain final concentration, and then the concentration gradient happens here in this location. So there are multiple factors that affect the diffusion. Temperature and diffusion coefficient is one of the important factors. And the diffusion coefficient that increases exponentially with temperature and is given by the equation D is equals to D naught exponential minus Q by RT. If you plug the log value of D with respect to 1 by T, which is inverse of temperature, you will see the linear slope here. The slope is given by minus Q by RT. So the thermal energy supplies the push that is needed to overcome the activation energy in case of diffusion. This is a practical plots for diffusion versus the inverse of temperature. And we can see that the hydrogen diffusion in FCC iron versus hydrogen diffusion in BCC iron, carbon in FCC iron, carbon in BCC iron, iron in iron oxide, iron in BCC iron, iron in FCC iron. So in this case, the steep slope like these ones, they denote that there is a high activation energy associated. So there will be more energy required to diffuse iron into face-centered cubic iron than compared to carbon into face-centered cubic iron. The other factor affecting the diffusion is type of diffusion itself. So in volume diffusion, the atoms move through crystal from one regular or interstitial site to another. And because of the surrounding atoms, the activation energy is large and the rate of diffusion is relatively slow. However, atoms can also diffuse along boundaries, interfaces, and the surfaces in material. Atoms diffuse easily by grain boundary diffusion because the atomic packing is poor at the grain boundaries. Because the atoms can more easily squeeze their way through the disordered grain boundary, the activation energy is low. Surface diffusion is even easier because there is even less constraint on the diffusing atoms at the surface. This table shows the type of diffusion versus the diffusion coefficient when there is a diffusion of thorium in tungsten in one case and silver in silver in other case. So you can see that for surface diffusion of thorium in tungsten, the value is lowest, and the volume diffusion the value is highest, and the change is almost double from surface to volume. Here in case of silver and silver, even the change is even drastic, with surface diffusion having only 0.06 while volume having 0.99. And similarly, the activation energy, change in activation energy is also drastic here. The other factor that affects diffusion is time. Diffusion requires time, and that is why the unit of flux itself has atoms per centimeter per second. If large number of atoms must diffuse to produce a uniform structure, long times may be required even if you are processing materials at high temperature. And some remarkable structural properties can be obtained if we try to prevent diffusion. For example, quenching of steel. Quenching is basically heating a material to extreme temperature, and rather than allowing it to slowly cool down, placing that heated material into either water or ice. So the steels that are quenched rapidly from high temperatures to prevent diffusion, they form non-equilibrium structures and provide the basis for sophisticated heat treatments. The other factor that affects the diffusion is bonding and crystal structure. The crystal structure and atomic size, they dictate the speed of the diffusion. Open structures such as the body-centered cubic structure allow faster diffusion than the closed packed structure such as the face-centered cubic. And we see that the similar diffusivity versus the temperature relationship here. They are both linear, but in case of carbon in BCC iron, we see that the diffusion is slow. Diffusivity line is increasing, while in the iron in FCC is steeper, meaning that the diffusion in this case is harder than the diffusion in this case. And that's because the atoms are not as closely packed as in the case of FCC. So the compact the atoms are in the structure, the harder for the diffusibility. That brings us to the other topic today, Fick's second law. In the Fick's first law, we saw that Fick's first law described the steady-state diffusion of atoms or molecules. In Fick's second law, it describes the dynamic or the non-steady-state diffusion of atoms. In real world, the temperature profile actually changes over time. In the first law, there was no consideration of time, so Fick's second law accounts for this and is given by the concentration difference is equals to 1 minus ERF divided by x divided by 2 root dt, where x is the depth of diffusion and d is the diffusion coefficient, and T is the time, ERF is the error function. And if you look into the curve, so depending on the time of diffusion allowed, the concentration over the surface over the depth changes. So if you have a lower time, the concentration only penetrates to some distance, and if you allow for higher times, the concentration goes more deep into the material. So fixed second law is actually derived just using this simplest version, where change in concentration over time is some diffusive constants, and then the gradient of concentration over distance, which is the simplified version of fixed second law. And in terms of concentration gradient and time, we can write this as Cs minus Cx divided by Cs minus C naught is equals to error function of x divided by 2 rho dt, where C naught, where Cs is a constant concentration of diffusing atoms at the surface of the material. So Cs, C naught is the initial uniform concentration in the material, and Cx is the concentration at location x after below the surface after time t. So from this equation, we see that to double the penetration depth, you need 4 times the time of diffusion. So you need to allow enough time for diffusion to for the material to really penetrate through the depth of the material that is going to be diffused with. So you might be wondering, what is the value of ERF, right? So ERF is basically error function, which is a mathematical function given as error function of j is equals to 2 by root pi integration of 0 to g to the power minus y squared dy. In this case, g is basically this coefficient here, x divided by 2 dt. And error function of 0 means 0, that is basically there's no penetration at the surface initially. And error function of error function of infinite means 1, which is deep into the material where diffusion hasn't reached yet. So let's look into some of the case studies here. One of the application of diffusion is in carburization. The objective here is to create a hard wear resistant surface while maintaining a tough ductile core. For this, the iron is heated in a carbon-rich atmosphere, and carbon diffuses into surface, which is caused using the interstitial diffusion, and we remove the material before the carbon penetrates too deep into the material. So by doing that, what we obtain is we obtain a high carbon case, which is the outer surface, and the inner surface is the inner of the material is not changed, which is still a low carbon core with ductile properties. The other application is precision doping in semiconductors. Here the application is creating PN junctions for transistors. In this case, the diffusion depth is limited to micrometers as compared to millimeters in case of the carburization of steel. We do precise control of temperature and time to determine the exact electrical properties. So in this case, we have a silicon lattice, and we diffuse dopant atoms, in this case phosphorus, to obtain the PN junction transistors for semiconductors. And sometimes we want to stop diffusion. So to keep these soda bottles fizzy, we want to keep the carbon dioxide in the soda bottles, or in case of chips bags, we want to keep the oxygen out of the chips bag. For that, we select a material such as plastic bottles that are manufactured with high packing density of the polymer chains, and those materials do not have any small micropores inside them where the gas can escape from. So basically, tight packing those bottles, we eliminate diffusion, ultimately keeping the soda frizzy. So two final terms I would like to go ahead and describe today are sintering and bonding. These are techniques that are used to fuse materials without actually melting the entire material. This is especially useful in applications where material processing by melting and casting are either hard or expensive. So this applies to many ceramics and some metallic materials where the melting points of those materials are too high for processing of the materials. Sintering is defined as the high temperature treatment that causes particles to join and gradually reducing the volume of pore space between them. When conducted properly, sintering will lead to densification of a powder to compact. Diffusion bonding is defined as joining process where welded parts are placed in close contact under controlled pressure and heated to a specific temperature, allowing atomic diffusion between the parts to create high strength joint. So this is given by this visualization. In the top one, we have sintering, which is powder metallurgy. So we have the different loose powders here touching barely at each other on the points, and then because the powders start to diffuse atoms to the contact points, they start forming this neck-like structure, and ultimately they diffuse fully, making a densified solid with small pores. So in this case, the driving force here is the reduction of surface energy. So the materials try to reduce their surface energy, and we get these densified solids. The other is the diffusion bonding, where we have two different types of metals, mostly metals. They have rough surface and they are pressed together at high pressure, and this is the microstructure view. So with naked eye, they seem like they are joint, but with naked eye we see so with the microstructure we see the gaps, and we apply pressure, and then because there are two different materials, so atoms try to diffuse from each other along these grain boundaries, and ultimately they give us a seamless interface. This has many applications. So for example, connecting titanium to ceramic, that is one of the example of diffusion bonding. If you want to explore more on the topic of the atoms and ionic movement in materials, please go and refer to the chapter 5 of the book. In next class, we'll be discussing the mechanical properties of materials from testing. We'll be discussing different types of testing that are done to determine the properties of materials. And for the lecture today, I'm skipping the quiz. We'll do this Kahoot quiz on the first thing in the next class. So with that, see you in class and have a great day. Thank you.